Hey folks, welcome to this episode on Vsepr. So what is Vsepr? It actually stands for the valence shell electron pair repulsion theory, and it's a theory used to predict the shapes of these molecules. It's all based on electrons, the bonding ones that are involved in bonds and the ones that are involved in lone pairs. So those are your non-bonding electrons as we see over here. Now the shape of a molecule is determined by the number of those bonding and non-bonding pairs and how they're kind of distributed around the molecule. Now, when we have molecules that only have one central atom, for example, all of these only have one central atom, so something that's bonding off of it, or that's acting as a kind of hub for bonding, then we only have one shape. When we have molecules with multiple central atoms, so we have long chains of atoms, usually they have a number of different shapes, and there's not an overall molecular geometry, there's just a combination of those individual shapes. So you can see here that we have different types of molecules and they have different names for that. Now this theory will help us figure out how to go from a Lewis structure into a more 3D molecule. So one thing that we have to keep in mind is, as you could probably tell, it's the valence shell electron pair repulsion. So we have to talk about repulsion a little bit. Now, when we talk about electrons, remember that they are all negative. Now we do have electrons when we have an atom bonded to a central atom. There are electrons involved. Now, if we have a single bond, there's only two electrons involved. If we have a double bond, there's two sets of those electrons. And again, if we have a triple bond, then there's actually six electrons involved in that bond. So the bonds are pretty negative because you have electrons involved there. And then if you also have lone pairs of electrons, well, those are also negative. So keep that in mind, and that will help you really go through how Vsepr really works. So what we call these negative regions caused by either electrons in a bond or non-bonded lone pair electrons, we call them electron groups, or sometimes you'll hear them as charge clouds. They might be used interchangeably, but they basically mean the same thing. The one thing that you have to remember is that they repel. Okay, they repel from one another, and because of that, they try to maximize the distance between them. Okay, so if you had a box like this and you start off with two electrons in the center, what they would do is they would try to repel from one another, and so they would end up on the corners of the boxes. Now this is a two-dimensional box, but if we have three-dimensional space, well, they can use up a whole different variety of angles to maximize that space. So here, if we look at balloons and try to figure out how this all works, if we have the two balloons, they're going to try to maximize the space. Now we're going to call this, where the knots are tied, as the central atom. So here we have our central atom and we have two other atoms on the side. So as you can see, the max amount of space is basically 180 degrees, as we can see over here. So these are two related. You have your central atom, your two different atoms, and they're separated by 180 degrees because that's the maximum amount of space that they can separate. Now, if you have three balloons, well, you can see that they're all in the same plane. They're all in one kind of triangle. They're not going up and down in all place. They're in a one plane, and the maximum of space that you can have is 120. So as we add more and more balloons, you can start seeing that the angles actually start changing. You go from 109.5 and 90, 120, depending on where they are, and to all of them being 90. So these balloons represent these electron groups, or these charge clouds, and you can see that as we add more of these charge clouds, remember that electron groups could be either a bond or a lone pair of electrons, and as we add more of them, the angles become smaller and smaller and smaller because they're trying to repel from one another to maximize the space between them. However, when we get into lone pairs, they actually take up a little bit more space. You can see this by this drawing over here. So all of this molecule of ammonia actually has four electron clouds. Now, where are they? Well, you can see one in the bond here, a second one here, there'd be a third bonded to there, and then you have your fourth one over here. But we have three bonds and one lone pair. It's still going to be four electron clouds. But the main thing that you see here is that this lone pair takes up a lot more space. And so what this is that as we introduce more and more and more lone pairs, it's going to actually squeeze these molecules closer to one another. So that means that the angles between them, they might have a set angle before. As we add a lone pair, that angle would actually get smaller because it takes up more space. Okay, in terms of more space, what we mean is that it's going to repel. It's going to repel these bonds a lot more than if this was just another hydrogen. So you can see here on the bottom there's a little chart in terms of repulsion. So when we look at bonding pairs and lone pairs. So these are going to be your lone pairs. You can see that your lone pairs and lone pairs, there'll be a huge amount of repulsion. The amount of repulsion between a bonding pair, so a bond and a lone pair, would be less than two lone pairs. And then finally, the repulsion is least when you have two bonds or two bonds that have electrons in them. That repulsion would be less than the other ones here. So here's a little chart about talking about the different types of geometries. Now we're going to go into this and explain some of them. As you can see, there's a difference between as what we call the steric number, and that's just the number of electron regions, okay, or electron groups. So in this case, where we have one group, two groups, that we get a steric number of 2. In this case, number 3 would be 1, 2, and 3. Now it's not just the bonds. Remember, it's the bonds and the lone pairs. So in this case, I have 1, 2, and 3 electron groups, and so my steric number would be number 3. But as you can see is that there's a difference in the name of the shape, because what the difference is between this and this is the kind of removal of an atom and replacing it with this lone pair of electrons. And as we said before, what this lone pair of electron does is it actually pushes these bonds closer to one another, and you can see that the bond was 120 degrees, but now we classify it as less than 120 degrees. So as you add more and more lone pairs, you start getting less and less of a bond angle between the actual atoms. Okay, so let's look at a molecule with two electron groups. You can see here that we have a central atom flanked by two other atoms here, and for example HCN or BEF2, and we'll come back to BEF2 in a second. Now you can see the maximum distance or degree that they would be separated is 180 degrees, so that would be their bond angle. Now in this case they have electron pair geometry, which has, you look at the electron regions, and that will show you as it's being linear. Now if we were to remove one of these bonds and replace it with a lone pair, it'd still be linear, but we don't have any lone pairs or anything like that, so both the electron pair geometry and the molecular geometry is going to be linear. Now, so what's the difference between electron pair geometry and molecular geometry? So our EPG, as we call it, electron pair geometry, is just all the electron regions. So in that case, that's going to be basically our equal to our steric number, okay, as we said before. Our molecular geometry, okay, is going to be looking at just the bonded atoms. Okay, so we actually remove the lone pairs. But what we don't remove is that we have to look at we don't show the lone pairs, but we show the effect that the lone pairs have on the bond angle. So as we said before, as you add more and more lone pairs, that bond angle between the atoms becomes smaller, so we will show that in terms of a degree number. Now we are going to be talking about hybridization a little bit later. This is called sp hybridization. You know that s only has one orbital. If we remember going back to our diagrams, we had our s, and then we had our p's, and then we had our 5d orbitals. Now in this case, it's very easy. If you count up the number of electron regions, here we have 1 and 2, well, all we do is we take our first orbital of s and our first orbital of p, so we call it sp, hybridization. That's talking about the hybridization of the central atom. This will be more clear when we get into hybridization, but it's just something that I'd like to show you in advance. Now, BEF3 is actually an example of this. BEF3 doesn't actually require 8 electrons in its octet. It only requires 4. So you can see that here you only have these 2 electrons and 2 electrons shared, so a total of 4 electrons, but it's still a stable molecule. Going into molecules that have 3 electron groups, this is called trigonal planar. So again, they're all going to be in the same plane. So if you were to take a side view of this, all you would see is your 2 green central atoms and your terminal atoms and your one massive central atom. And that's all you'd see is actually be in the same plane. But when you flip it up, you'll actually see this configuration here. The maximum amount of degrees that would go between that is 120 degrees. So when the structure is the same as your electron pair geometry, so 1, 2, 3, you'd have a steric number of 3, that would be your EPG. And because there are no lone pairs, your molecular geometry is the same as your electron pair geometry. However, when you get into This one over here, you still have three electron regions, 1, 2, and 3. So you're still going to be, your electron pair geometry is going to be trigonal planar because you can still recognize that there are three regions of negativity. However, remember that for our molecular geometry, we actually discard this thing over here and we just look at the bonds themselves. So in this case, what we're going to have is we're going to have a molecule that's called bent. Now, again, as we add this lone pair here, remember that the angle that was here, that was 120 degrees, is actually going to get smaller because it's going to push these bonds down. So this angle will be less than 120 degrees. Now, again, the hybridization, you can see that we have three regions over here. So our first orbital of S, and then there's two orbitals of P, so it's going to be sp2. When we get into 4 electron groups, we can see that our name is tetrahedral, and the angle has decreased to 109.5 degrees. And so again, here you have 4 negative regions. In all of these, you have 4 negative regions, 1, 2, 3, 4, and 1, 2, 3, 4. So they're all going to have electron pair geometry of tetrahedral. However, the molecular geometry changes. This will still be tetrahedral because you still have your 4 areas. But here we've added a lone pair. That's going to actually make it into a trigonal pyramidal. Why trigonal pyramidal? Because you have 1, 2, 3, and it's going to, if you kind of add the sides here, you would have 3 sides that look like a pyramid. And finally, this last one over here, you have bent. So again, you'd only see those 2 bonds over here, so you're going to have a molecular geometry of bent. Again, as we add this, we're increasing the repulsion. Okay? And so what that means is that these lone pairs are going to push on these bonds over here and make them squeeze in a little bit tighter. So you can see that with the angle over here, your bond angle is less than 109.5, and this bond angle is less than 109.5. Basically, what we can say is that this is going to be approximately 107 degrees, and this is going to be about 104.5. For every lone pair, you're basically decreasing about 2.5 degrees. So that's how you get the 107 and the 104.5. Hybridization is sp3. You have basically you have 3 regions over here, so you'll have 1s and 3 p's to equal 4 regions of charge. So 1, 2, 3, 4. So if you remember, that's going to be like s1, 3, 1 plus 3 is going to equal 4. When we get into the 5 electron groups, again, something interesting happens here. So what we do is we call these different bonds. The ones that are kind of circular around this way or around here, these are called your equatorial bonds, and then these ones over here, those are going to be your axis bonds, and again, these 3 over here, those are going to be your equatorial bonds. So what happens is, again, these are called trigonal bipyramidal. So if you kind of connect the dots over here and then make this into one, you actually see that you have kind of 3 faces of the triangle, one face here, one face there, and then one face in the back. And then you not only have one of those, you actually have the same thing on the bottom. So that's why it's trigonal bipyramidal. As we have no lone pairs, the molecular geometry is the same as the electron pair geometry. But as we add lone pairs, you can see that they take a preferential position. They actually take a position on the equatorial position because there's a little bit more space. This angle here between this and this is actually 90 degrees. The angle between these is 120. So there is a lot more space between these different atoms in the lone pair rather than this one over here, that'd be 90. So they'll take a position up in the equator before they'll take an axis position. And you can see here that, again, our molecular geometry changes based on where it is. So this turns into like a seesaw, if you will. Like this would kind of be the legs, and you have people sitting on here, people sitting here, and going back and forth. So it's a seesaw position. Here you have a T-shaped. So again, you can only see these T-shaped over there. And then you can actually create a linear shape with 5 electron groups because all of these are occupied by lone pairs. The hybridization is sp3d, so you have 5 regions of charge, 1, 2, 3, 4, and 5. So s1, p3, and then you'll need a d1, so 1 plus 3 plus 1 gives us 5 regions of charge. And the last one that we're going to be looking at, we just took a sampler of of the different ones that you can find, or the different molecular geometries you can find in this group. But in this case, they're octahedral. And the reason for that, if you connect the dots, one, two, here, and then the back, and you create a pyramid, it's kind of like, you know, the Egyptian pyramids of Giza. You have a four-sided, and then if you have the same thing on this bottom side, you'd also have that same, so you actually have that octahedral shape. You have 8 sides to the pyramid. So again, your molecular geometries and EPGs are going to be the same. In this case, your bond angles are all 90 degrees, and your hybridization is sp3d2 because you have 6 regions of charge. Now again, in this case, what you're going to see is that the lone pairs will actually take up an axis position, but it doesn't really matter. Sometimes you'll see them out over here, sometimes you'll see them over here. Because all of these angles are 90 degrees, they're going to be equivalent in terms of distance. So some textbooks you might see this, or some people might see taking them first or that. Just remember that all of these angles are the same, and so there's not one that has more room. But we're going to be doing it in terms of the axis first, however, which one's up and down, and then going into the equatorial positions. This is called your square pyramidal because you'll connect your dots here, you'll create a square, and then if you connect them with that central point here, you're going to create a square pyramid. And here, you actually create a square planar. You just kind of connect the dots. There's nothing else to do. You actually just create a square in the same plane. So how do we go from a Lewis structure into this Vsepr structure, a 3D structure? First of all, draw the Lewis structure. You have to do the mathematical method of that. And then determine the number of electron regions by counting up your bonds and your lone pairs. So in the case of here, we have this, and this. That equals 4 regions, and that's going to be our steric number. So our steric number tells us which electron pair geometry that is. Now, after doing that, we have to take into account our lone pairs, because that will create our molecular geometry and also give us an idea of what the angles are going to be. So before we do an example, I just want to give you a quick note on resonance structures and bond types and how they affect the angles. When we talk about bond types, you might have a double or a triple bond. Remember that these double bonds are sharing 4 electrons instead of just the 2 found here. And then triple bonds would be sharing 6 electrons instead of just the 2. Now, if you have kind of 4 electrons in this one region, they're going to be doing a lot of repulsion. And so what they're going to do is, because they're going to be taking up more space and repelling the other bonds more, what you're going to find is that this angle between the hydrogens is actually going to decrease. Now, this is a trigonal planar, and trigonal planar should have 120 degrees between them. But again, that difference from what we actually see versus what we propose is due to this double bond that's going to be made up of more electrons and therefore taking up more space, creating more repulsion. When we talk about resonance structures, remember, in this case, this is nitrate. So nitrate with the NO3 1 minus, so there'd be a 1 minus over here. This bond moves from this area to that area, and then here and here. So the resonance structures just keep moving these delocalized electrons around and around. Now, as a result, this actually creates bonds that have equal lengths. So resonance structures, you'll have all these different nitrate groups, or the different arrangements, all having the same bond length. So it kind of goes away from here, or kind of is a little bit different, because this is only one structure, but because these are delocalized electrons, they're going to keep moving around. And so remember that they have these resonance hybrids, where you'd have these kind of dots here showing that all these bonds would actually be the same. So let's do an example here. Here we have PF3. So it says determine the EPG, the MG, and the bond angles for PF3. So the first thing we need to do is do our Lewis diagrams. And so in this case, we need to do the mathematical method for doing this. So I know I have phosphorus and I have fluorine. I have 1 and 3 of this one. This one has 5 5 valence electrons. This one has 7. So here I have 5, and that's going to be 21. So altogether, I have 26 electrons to work with. Now, if they all had octets, 1, 3, so this one requires 8, so it's going to be 8. This also requires 8, so that's going to be equal to 24. So altogether, that's going to be 32 electrons that would be needed. So they're going to obviously have to share. 32 minus 26 will be equal to 6 divided by 2. So I'm going to have 3 bonds. And last but not least, I'm going to have my 26th minus 6, and that's going to be 20 divided by 2, and that's going to be 10 lone pairs. So my phosphorus has the most unpaired electrons, so it's going to be in the middle, flanked by the fluorine, fluorine, and fluorine. So those are my 3 bonds. I can get rid of those. And my electrons here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And last one is 10. So all of these all have octets, octet, octet, octet. So I can get rid of my lone pairs. So now what we have to look at is we have to figure out what our EPG is, our electron pair geometry. So our electron pair geometry will be based on our steric number. So we have to count up how many charged regions there are around the central atom, our central atom being phosphorus. So I have 1 bond here, 1 bond here, 1 bond here, and I also have this lone pair. So my EPG is 4. Now if you go back to the chart, EPG of 4 would be tetrahedral. Okay, so tetrahedrals, they all have bond angles of 109.5 degrees. However, when I look at my molecular geometry, well, this is going to be different because I actually have 1 lone pair of electrons. So that means that my molecular geometry will not be the same as my electron pair geometry. Now, if you go back to the chart with that, when you look at 1 lone pair, this is actually going to be trigonal pyramidal. Okay, so if we were to draw this a 3D structure, we'd have our phosphorus here, we'd have a fluorine in the same plane, and then we'd have a fluorine coming out towards you, okay, our lone pairs, and then we'd also have a fluorine going into the back of the page, like that. Okay, and you'd have that over there. So it actually does look like a pyramid. So if you kind of connect this, this, and this, and then connect it to that, you have a 3-sided pyramid, and that's your trigonal pyramidal. Now, larger molecules might have more than one central atom. In this case, when we look at the 3D structure, the 3D sketch over here, we have carbon, carbon, and oxygen. All of these are going to be central atoms. So we actually have 3 central atoms. Now, there's no overall geometry for this molecule, but what we have is we have a geometry for each central atom. So technically, the geometry of the molecule is the combination of these individual geometries. So if we look at this over here, you can see that carbon has 4 central or 4 charge areas, 1, 2, 3, 4. So it has a steric number of 4. That means it's going to be a tetrahedral. Okay, hedral. Now, because it doesn't have any lone pairs here, it doesn't have lone pair anywhere there, its molecular geometry will also be tetrahedral. Same thing for this carbon, 1, 2, 3, 4 areas of charge, so its electron pair geometry is tetrahedral, and because it doesn't have any lone pairs, the molecular geometry will also be the same. So that's both for this one and for this one. Now, when we look at this oxygen, we can see that we have 1, 2, 3, 4 areas of charge, so that our EPG is going to be tetrahedral, but however our Mg will be different because we see that we have our 2 lone pairs. So a steric number of 4 with 2 lone pairs, that's going to be called bent. So let's look at an example here. Let's determine the EPG, the Mg, and bond angles for each of the following molecules. Now in this case here, we have to look at how many central atoms we have. We have oxygen, carbon, carbon, and nitrogen. So again, we have to look at our different areas for our EPGs. We have to look at how many charge areas we have, and for our MGs, how many bonds we have. So if you can look at this, oxygen here has 1, 2, 3, 4. So its EPG is going to be, I'm just going to do this over here. EPG is going to be tetrahedral. Okay. And its Mg is going to be bent because it has 2 lone pairs. So that means that the bonds between the oxygen and the carbon over here, that's going to be less than 109.5, which equates to about 104.5. Now let's look at the carbon. So the carbon over here, now it has 1, 2, 3 charge areas. Okay, so something that has 3 charge areas is going to be trigonal planar. Okay, now because that carbon doesn't actually have any lone pairs around, the Mg is also going to be trigonal planar. So that means that when we look at this carbon, and oxygen, all these things will be in that same plane. Now let's move on to the next carbon over here. So that carbon has 1, 2, 3, 4 charged areas or electron regions. So again, the EPG is going to be tetrahedral. And again, it has no lone pair, so the Mg will also be tetrahedral. We don't see any lone pairs around this carbon. And finally, let's look at that nitrogen here. One thing about this, these are all going to be 120 because they're trigonal planar, and the tetrahedral will be all 109.5 degrees. The last one, the nitrogen, you can see that it has 1, 2, 3, and 4. So again, this EPG is going to be tetrahedral. But the Mg will be different because we can see that it has one lone pair. So when it has 1, 2, 3, 4, it has a steric number 4 with one lone pair. This is going to be trigonal pyramidal. And because of that, it's going to be less than 109.5. Why 109.5? Because remember, tetrahedral is 109.5. So if it's less than 109.5, it's going to be approximately 107 degrees. So that's it, folks. Thanks very much for watching. Hopefully this helps, and we'll see you next time. Thanks.